It's my pleasure to welcome you to this final topic with me. We're looking at forces, couples, and their systems. Well, this is a concept that you're already familiar with. For instance, in your elementary physics, you talked about moments, which is the turning effect of a force. We know that the turning effect can be clockwise and can be counterclockwise. When it is clockwise, conventionally, that is taken as negative. And when it is counterclockwise, we take that to be positive. To now find the magnitude of the moment, we all can recall that that is a product of the force and a perpendicular distance from the point about which the force is causing a turning effect. So that point about which the force is causing a turning effect is called a pivot. So we take a perpendicular distance from the pivot to any point on the line. Um, you know that whatever point you take on the line, the perpendicular distance will be the same. I'll show this in the next figure. Now, if you look at this figure, we have a force F, that is the red line, and we're trying to find the moment of that force about the pivot O. The distance, the points A, B, and C are on the line. And you recall that we can write that force in vector form. Once we know its magnitude and we know any 2 points on the line, we can find a unit vector along that line, multiply by the force. That gives us that force in vector form. Now the perpendicular distance is the h. This h can be calculated either from OA. Once we know the angle OAF, which is the angle the line OA makes with the force, so that would be F times OA sine angle theta A. Similarly, we can find H by finding the angle that OB makes with the line, and that would be F sine theta B. Or the moment is also force times perpendicular distance formed by OC, which should be OC sine theta C. So whichever of the lines that is used, we still get the same value for H, because we know, though the length of the line is changing, OA is different from OB and is different from OC. As the line changes, the angle of inclination also change. So that makes H to remain the same. So with this, we can find that the moment of the force is F times H, where that H can be calculated as OA sine theta A, for instance, or it could be H equals OB sine theta B, and so on there, with as many points as we may have on that line. So simply, it is we can redefine moment to be the magnitude of the force multiplied by the perpendicular distance formed by a line run from the pivot to any point on the line. So whether OA, OB, or OC, or any such point that is on the line. So we can write vectorially. In vector form, we can therefore say that moment is F times R sine theta. But to recall that in vector form, the vector product of R or F is moment of R times moment of F sine theta. If you rearrange this, it will be R sine theta times F, where you remember R sine theta is actually our H. So we can actually now write moment as the vector products of the radial distance and the force. All of them now in vector, R in vector, ROA in vector, F also in vector. By the time we do this, the magnitude will be given as magnitude of R times magnitude of F sine theta of the angle between them. And fortunately, in vector form, we don't need to worry about whether it's clockwise or counterclockwise, because once we perform the vector operation, it will bring it out clearly, whether it will be negative or positive. Then you can interpret. If it is negative, you know then it is clockwise. If it is positive, then you know that it's counterclockwise. I think you recall that in doing the vector product for um, three-dimensional problem where you have IJK, you may need to use, in fact, you will need to use your matrices. That will help you to be able to do the computation very quickly. Going further on this topic, we can now try to look at some other concepts that we need to be familiar with. For instance, uh, if you're trying to find the moment of a force and the force is at an angle, we can break the force into its components. For instance, you have a force that is along x and y. So you can find the moment of Fx along about the point and find the moment of the force Fy along about the same point. Now, by the time you add up the moments, it gives you the moments of the two components. Uh, this concept is due to Varignon, which says that the moment of component of a force is the same thing as the moment of the resultant force. So in analysis, when we are faced with rather complex forces, we can break them into components, find the moment of the forces, say, along x about the point, and also the moment of the forces along along y about the same point. Then we can summing up vectorially, knowing that one may give us positive, or both of them positive, both of them, or one is positive, that is negative. So that idea that we can break forces into components to find the summation of the moments is the Varignon's theorem. The other way is that we can slide the force from its indicated position until it hits one of the axes, so that the components along, say, x, the moment of component along, say, x, passes through the pivots. And you know, when a force passes through the pivots, the moment of that force about that point is 0. So we are then left with only the y components, or vice versa, or slide is such that the y component passes through um, the point of pivot, and so the moment of the force along y then becomes 0, while that of x will then give you the total value. So that is the principle of transmissibility. We will talk more about this or understand this better when we try to look at examples of these two concepts. Well, we have dealt with resultants of forces before now. We can add up forces, adding them up vectorially, either graphically or adding them up vectorially, breaking them into various components. The only caution is that remember that you have to add up forces along the same axis together, and then by the time you sum up, for instance, we have a force broken into Fx and Fy, and another one Rx and Ry. You can add Fx to Rx and Rx to Fy, not Fx added to Fy. So that by so doing, you can find the summation of the forces, simply written as sigma from 0 to n, from Fx, Fy, and then you can move on. You can also do the same thing when it comes to moments or wrenches. We can always add up these components, whether you are dealing with wrenches, whether you are dealing with forces, you can always add them together by taking the components separately and adding them on. If a system is in equilibrium, then it means the summation of the forces will be 0. This you know very well, this back in the secondary school. And if the summation of the forces is 0, does not necessarily mean that the force is in equilibrium until summation of the moments is also 0. So two important conditions for equilibrium. Summation of the forces must be 0, and summation of the moment must be 0. Because as we have seen in couples, summation of a couple, forces in couple is 0, but it's turning. Just like when you are handling the steering of the vehicle, you are turning up with your right hand and pulling down with your left hand, equal forces. But the vehicle is turning because you are applying couple. One is turning it to the right, the other is turning it to the right. And so you get a turning moment. So for equilibrium, I emphasize the summation of the forces must be 0, as well as summation of the moments. We will see how these concepts are to be applied in practical problems. Next class. I think with this short video, you can go back, read the note again, try to lay your hands on the examples. We'll look at 2 or 3 of them in class, and I would expect that you'll be able to resolve the rest on your own. So, ladies and gentlemen, thank you for your attention. Good morning or good day, or whatever the time is with you. Thank you.